So again, good afternoon, everybody. Today we are continuing series, which I can tell you all are just absolutely loving. And we got to do comparison test and alternating series test. Now, I personally think of all of these tests, the limit comparison test is by far the most powerful. The general comparison test, not so much. So what does this do? Well, the comparison test takes a convergent or divergent series and compares it to another series, and then we can use that relationship. So here's an example. It says we've got a series that's the sum from the sum of 1 over n cubed plus 1. Well, notice, when n starts to get above, 4, 5, 6, that 1 doesn't make a whole lot of difference. So we could compare it to the sum of 1 over n cubed. And if we do that, right, that's what's called taking the dominant terms in both the numerator and denominator. So obviously there's only one term in the numerator. The dominant term down here is obviously n cubed. That's the only thing that changes. And the reason we want to do something like this is we know this is what kind of series, guys? So good. That is a p series, correct. All right, it's n to the p power. Some of my students last semester thought it was funny when I referred to the p series as the p test. So we could compare that guy to this guy. We already know this behavior, and if we prove this does something, then using one of these two comparison tests, this will follow. So we've got to start with the regular comparison test first, which is a little harder to prove. And again, I apologize for all these rules, but this is just how series are handled. Now, comparison test has two sets of rules. Or there's two bullets, but each bullet point has two parts. We're given a sum of some a sub n. We create the sum that is b sub n. Okay, so we're given this one. We make this one on our own. If we show that the sum of b sub n converges, we can't just automatically go to a sub n converges. We have to also show that this summation is less than or equal to that summation. Now it says for all n, but those kind of things are a little, let's say, lackluster in terms of how strongly they hold up. So let's not worry about that so much. The second one says if b sub n diverges, we must also show that the sum of a sub n is greater than b sub n. Then a sub n also diverges. So you just give me 1 second here. I want to find my notebook, which I'm hoping my dogs did not take off with. Here we go. Let's see if I have these in here. I'm trying to minimize the mistakes that I make. All right. So the first one, we're given 3 over 2n cubed minus 17. So I need to find a series that is closely related to that. And remember, we're taking the dominant terms. So this is a sub n. I need to find b sub n. Well, b sub n contains the dominant terms, which are 3 on top, and obviously the 2n cubed on the bottom. So by dominant, we're obviously talking about which one is bigger or smaller, right? Which one makes the greater changes, that sort of thing. So I've got 3 over 2n cubed. I can rewrite that as 3 halves sum 1 over n cubed. You should recognize that as a p-series. Okay, so this is p-series. P is equal to 3. That's greater than 1. Does that mean converge or diverge? Okay, I see one answer so far. Anybody else? All right, good. So that means that that series is convergent. Which means I now have to compare it to the original. So b sub n converges, which means I now have to prove this guy. So is this true? Well, one way we can do this is to look at a few of the terms. So one suggestion I can give you is to do this. Look at the first 10 terms or so of both of those and add them together. So this is sum. It starts at 3. So we're going to go to 12. And that's 3 over 2n cubed minus 17, less than or equal to sum n equal 3 to 12. And this one here is going to be 3 over 2n cubed. Now, how do we do that? Let me find my calculator. Okay. So in my calculator, come over here so you can see. Turn this light on in case we need it. Alright. Guys can see the screen? Okay, so I'm going to go to Math. Then I'm going to go to option 0 or 10. When I do that, I get a little summation symbol with all the inputs. Now that's if you're using an 84 plus. If you are not, then set up a meeting with me and I'll talk to you about how to do this on an 83. So has everybody got that guy that's wanting to try it? Why did I use 12? So 12, what's 12 minus 3 plus 1? Right? There's a counting principle that says if you want to know the amount of numbers between two values, you subtract the 2 and then add 1. So I had said to use approximately the first 10 terms, so that's why I did that. So did you guys get this summation? So I'm going to then put in x equals 3 on the bottom up to 12, and then I'm going to do 3 divided by 2x cubed minus 17. So I'll do that summation and hit enter, and then I will hit second enter, which pulls up the same thing, and I'll get rid of the minus 17 and run it again. So if I do that, it looks like out of the first 10 terms, the original sum is slightly larger. So I'm showing that a sub n is bigger than b sub n. But what I wanted to prove was the opposite. So what does this tell us? Well, unfortunately, it's inconclusive. Right? We've got to meet both of these criteria for it to give us something. So inconclusive. All right. Another way we could do this is sometimes we can look at the terms. Okay? So over here, every term in this sum, I'm taking 17 away from the denominator, which means this denominator is going to be slightly smaller than this one, which means every term in this sum is going to be slightly larger. Right? If I divide by a smaller number, I'm getting bigger numbers. If every term here is slightly bigger, well then the sum of a sub n is probably going to be bigger than b sub n. And if that's the case, well, that's not what I was looking for. And so this turns out to be inconclusive. So it says, so we need to compare this test to a more reliable one to use it. We're not comparing it to another test. The test in itself requires that you first show the series that you come up with, b sub n, either converges or diverges. And you can do that by using any test. So this is why I say that the comparison test is not exactly the greatest one to use. Sometimes you might need it, but it's not the most reliable. And it's very hard to interpret. Am I okay to erase that so I can do the second problem? All right. Thanks, guys. Thanks for being responsive and active today. All right. So part B. So I like to give this problem to you guys, typically, because I want to see what you come up with. So again, we have to come up with the dominant terms. What is dominant on top? Is it 2 or is it sine squared? Okay, can you explain why you said 2? Or if you said sine squared, can you explain why you say that one? So I see a couple responses. Sine goes to 1. So yes, sine, right, is buried between 1 and -1. And if I square it, well, then it's bound between 0 and 1. So yeah, good job. All right, so 2, obviously, right, this thing, as we were saying, can't be any more than 1 at most. So the dominant term on the top is 2. Okay. On the bottom, does 5 to the n get bigger, or does n? Well, that's pretty easy, right? That's going to be the exponential. So 5 to the n. What kind of series is that? Ah, I gotcha. Gotcha already. So remember, a p-series is that you've got n to a power. If n is the power, it's geometric. So if you want, you could throw that 2 out front, or that could be your a, and you have 1/5 to the n, right? Can you guys see that okay on your screen? It doesn't look too bad, I don't mind. All right, so that's geometric, which means r is 1/5. We need the absolute value of that to be less than 1, which it is. So our b sub n converges. So if b sub n converges, again, we are trying to show that a sub n is less than or equal to b sub n. So I want you guys to plug that in for the first 10 terms and tell me what you get. While you're doing that, I'm going to do it an alternate way. I'm going to plot the two functions and look at the values of the sum, or at least each value that's given for the function. And if they are all bigger for a single equation, well, then that equation must be the series that we're looking for that's larger. And then if you could just give me an approximation of what you get. I don't know if that helped at all. So you got that b sub n was greater. Okay. So let me see what comes out here in my picture. So of the graph, you have to zoom in quite a bit to see the graph. You get this behavior for a sub n. Let me just do the plot one more time. You just confirmed that your answer is correct? Turn it, I just did the graph twice. Hold on a second. Alright, so there's a sub n. Okay, so b sub n does this. It comes in above, goes below, and then they kind of start to level out. So from the graph, it's a little hard to tell. I believe that if these values are larger, as long as the disparity here is less than up here, then b sub n would be bigger, so maybe a better check would be to plug the numbers in. You're telling me that b sub n is greater, which is good. That's what we were trying to show. Right, if a sub n is less than b sub n, that's the same thing as saying b sub n is greater. And the reason for that is we've shown b sub n converges, and we've shown this. Therefore, a sub n converges. So what I would like you guys to do is, at the end of the problem, say, therefore, by the comparison test, a sub n converges. And I want you just to get in the habit of doing something like that, because when it comes time for the exam, I'm going to ask you to tell me what test did you use, and then does it converge or diverge? So I got Ken saying his were a little different. Okay. So typically just the first 10 terms should be fine. So plug in 1 to 9. 1 to 10 is fine too. That's 11 terms. Doesn't matter. Just don't overwhelm your calculator, which is why I say typically use the first 10. The only thing that might be a problem is you might get confused as to which one is which. Right? So the one that we start with, that's a sub n. B sub n is the one we create. Yeah, n equals 1 is fine to start with. That's where this sum starts, right? N equals 1. And again, we can do this kind of as an argument. How would you enter sine squared of x in the summation? All right, so let me do it real quick, since there seems to be some disagreement. All right, so go to math, go to option 0. X or n, whatever you got in there, doesn't matter. Starting at 1, running to 9 or 10, it doesn't matter. And then the first one is 2 plus, you could just do sine of x, close the parentheses. If you want, you can put another set of parentheses around it and square the whole thing. And then all of that divided by 5 to the x plus x. Okay, so I got 0.577 for the first one. And if I rerun it, taking away the sign, and the x term, I get 0.49 or 4999. So yeah, I did get that A was greater. Which means this does not converge, right? This diverges. So out of curiosity, I'm going to drag that out a few more terms just to see, but I'm pretty confident that that's fine. So let's go out to, I don't know, 30 terms. Well, yeah, it's already accurate to the right decimal place, so. Yep, even 30 terms, it's still bigger. All right. So let's see if we can find one that converges, right? Let's see if we find one that makes some sense. So far, the first two haven't met the criteria, right? Because we've got to have both. All right. Again, we have to make up b sub n. That would be 2 over root n here. Okay. We've got to prove that this thing converges or diverges. So I'm going to rewrite it as n to the 1/2. So yeah, this is p equals 1/2. This is a p series, right? It's n to a power. So p equals 1/2. That's less than 1, which means diverges. Okay, so if that diverges, what we would like to happen is for a sub n to be greater than b sub n. Okay. So again, let's take the first couple terms. So sum n equals 2 to 11, 2 over the square root of n minus 1. Find a number for that. Then from 2 to 11, 2 over square root n. And find a number for that. So let's do that real quick and see which one's bigger. Darn it, I keep starting my sum at 1. There we go. And then do it again. Oh, that's not the right number. Darn it. Okay, there we go. And then do it again. Get rid of the -1. Okay. So I got 17.6 and 8.6. Something like that. All right, approximately 17.6 and 8.6. Which means A is greater than or equal to B. And that's what we wanted to prove, right? So if this diverges and this, by comparison, summation A sub n also diverges. All right. So that's comparison test, right? It's not fun. And I'm guessing you're probably not going to like limit comparison too much because it requires a decent amount of algebra, but it is much more definitive. All right. So let me get rid of this guy and let's take a look at the limit comparison. So this is the limit comparison test. Now it states that we have any two series that have positive terms. Again, B sub n is the one that we're going to come up with using the dominant terms. Then if we take the limit as n approaches infinity of the division of the two sequences, right, the two insides of the sum, and we get back a constant. And they tell us all this stuff, right? It says where c is real and where c is greater than 0. All that means is we get back a number, right? A non-negative number. And obviously it has to be real. Then both converge or both diverge. So once again, the B sub n that we're comparing it to, we have to prove what does it do first. So again, let me demonstrate. Taking the dominant terms, this is going to be 2 over 4 to the n, or 2 times 1/4 to the n. We know that to be a geometric series. R is equal to 1/4 and the absolute value is less than 1. Let me ask you, does that mean converge or diverge for B sub n? Okay, got one answer. Anybody else want to weigh in? Right, so this is converge. So B sub n converges, which means if we then can prove this, A sub n will also converge. So now I need to take limit as n approaches infinity. I need A sub n on top, so 2 over 4 to the n plus 2. And I'm going to divide by 2 over 4 to the n, or if it's okay with you, I'm going to multiply by its reciprocal. That's really nice because I can get rid of those 2's. But then I have to evaluate a limit. So this one might look a little strange, but we can go ahead and divide by the highest power, or the biggest term everywhere. So this would be limit as n approaches infinity. I'm going to divide every one of these terms that remain by 4 to the n. So what do you think that comes to if I let n approach infinity? So yeah, this goes to 0, but the whole thing goes to 1. So, is 1 a constant that's real and greater than 0? Darn right it is. Therefore, by, let's say, LCT, limit comparison test, A sub n also converges. Good, bad, doesn't make any sense, makes great sense. Be quiet and do another one. Why did you do the first part? So the test says they both have to do the same thing. So whatever I make up, right, and I'm not making it up, I'm taking it from the dominant terms, but whatever I come up with for B sub n, if it converges and I get this greater than 0 and a real number, then the original converges. If B sub n diverges, I get this, A sub n diverges. And then the other situations would be I get converge or diverge here, but I get a number that's complex or infinity, something like that, well then I can't tell anything about the other one. All right, we've got n squared over n to the fifth plus 2n minus 1. I have to first come up with something to compare it to. So the dominant term in the numerator is obviously n squared. And the one in the denominator is n to the fifth. I can simplify that. That's 1 over n cubed. That is yet again a p series. That's greater than 1, which means converges, right? Next step is to take limit as n approaches infinity of a sub n divided by b sub n, or multiplied by the reciprocal of b sub n. So I'm going to multiply by n cubed over 1 as opposed to dividing the entire thing by 1 over n cubed. So at this point we have to just recall how to get our limit. It's an infinite limit, so divide by the highest power of n, which is n to the fifth. That would leave me with 1 up top. This would become 1. 2 over n would become 2 over n to the fourth. And then negative 1 would be negative 1 over n to the fifth. If I take the limit and anything is divided by n to a positive power, that all goes to 0. So I get 1 again. That is a real number that is greater than 0. And if that's the case, then both series do the same thing. The b sub n converged, therefore by limit comparison test, a sub n converges. Tom, there is no reason why you couldn't do that. And that might actually be a good step if you're taking an exam. Right? Because the trick is, I'm not going to tell you what kind of series it is. You're going to have to look at it and say, I got to use this type of test. Okay, so we've got, looks like one more here. Anybody need any more time with this one, or we go to a race? Alright, so I'm assuming we're good to erase. I can look at that after we're done if you like. Off the top of my head, I do not know. But we still have quite a bit of tests to do before that. Yep, no problem. All right, so let's see if we can figure this guy out. I need to first come up with B sub n. So my question to you is, what is the dominant term on the bottom? Is it square root n or square root n plus minus 1? So square root, right? If I just pick a number like 9, square root of 9 is 3, square root of 8 is 2 root 2, which is actually a little smaller. So we want the dominant terms of square root n. 1 over square root n, okay. Let's go ahead and determine what does that do. Well, that's n to the 1/2. It's a p series. P equals 1/2, less than 1. That diverges, right? So good, good. All right, so then let's go ahead and do that case in the middle, right? So limit n approaches infinity, 1 over square root n plus square root n minus 1 multiplied by square root of n over 1. So again, this is all n to the 1/2 power. So I'm going to divide every single term by square root of n. Which gives me that. Simplifying. Alright, so I divided everything by root n. This divided by root n is 1. That's 1. That I rewrote as n minus 1 over n to the 1/2. Then I broke this into two fractions, n over n and minus 1 over n, which turns out to be 1 minus 1 over n. If I apply the limit now, 1 over n goes to 0. 1 to the 1/2 power is 1. So I end up with 1 over 1 plus 1, or 1/2. That is a real constant. That is greater than 0. So if the series I came up with diverged, so does this one. Everybody good with that? Seems like everybody's following along pretty well today. That's what I wrote, Parthie. You can't read it? Man. Some really weird shadows in here. Clearly that's what it said. All right. So those were comparison and limit comparison. I would like to start and possibly finish alternating series today. You know, I mean, it could have been something with the camera, with it focusing and defocusing. You do a lot with light tricks, guys. Don't forget, I studied optics. Alright, so way back when we started all this stuff, right, when we began with sequences, I eluded the idea of an alternating series. Alternating meaning that the signs of each subsequent term is opposite. So if we start with positive, it goes negative, positive, negative, positive, or vice versa. So you can see that here, right? This has an alternating term that makes it plus, minus, plus, minus. And just like all the other series we've studied so far, these don't always converge or always diverge. We're given here a list of alternating terms. And let me look at this last one here, because I recall that it was wrong in my original packet. And I want to make sure that it's correct. So if n is 1, we get 4 pi over 2. If n is 2, so this is always going to be 0. So yeah, let me fix that. I had a feeling that was still incorrect. So let's see, if we make it n pi over 2, pi over 2, that's 1. 2 pi over 2. Nope, it's got to be... Is it n plus 1? It's got to be odd numbers. So wait, I guess I did have it right, didn't I? Let's see, n equals 1. You get 3 pi over 2. If n equals 2, you get 5 pi. Yeah, I was doing some weird math in my head. I did fix it. Good Lord. What's that, Parthie? On my magic notes, I have sine n pi over 2. So yeah, see, I did fix it. Okay. So yeah, it's got to be right. It's got to be pi over 2, 3 pi over 2, 5 pi over 2, and so on to get 1, negative 1. So that is correct. All right. So how do we do alternating series test? Well, we've got to do two things. The first thing is we've got to show that a sub n plus 1 is less than or equal to a sub n. What does that mean? Well, that means that the term that comes next has to be smaller than the term that came before it. And how can you satisfy that for me? You can plot it and show me that it's a decreasing function. You can also use calculus to do so by taking the derivative. The important thing here is note that there's absolute values. The whole point of those is to strip away the portion that makes a series alternating. So once we discover that it's alternating, we need to get rid of that portion and then test it. So again, we need to show that the subsequent terms are smaller than the ones that came before them, and the limit as n approaches infinity goes to 0. If we get both of those, then we can say it's convergent. If either of them fail, we're going to say that it is divergent. And by the way, the rest of these terms just alternate between 1 and negative 1. These are just all the different forms that I'll show you. There's many different forms, but I think that's the extent of the ones I'll give you. Okay. Determine if the alternating series converges or diverges. So we know it's alternating because it has this cosine n pi. So a sub n is cosine n pi over n. The absolute value of a sub n is 1 over n, because the absolute value gets rid of the alternating portion, which is cosine n pi. Right? If that thing goes between 1 and negative 1, and I take the absolute value of it, it's always going to be 1. So I've got 1 over n here. I also need a sub n plus 1. Well, that's 1 over n plus 1. So I want to show that this thing is decreasing. And as I said, for me, it is enough for you to show me a sketch. So what does the function 1 over n look like? Well, we should know that that looks something like this. So clearly, this is decreasing. And the second part says, take the limit as n approaches infinity of a sub n, right? So if we just scroll up real quick, right, of a sub n, or the absolute value of a sub n. Absolute value of a sub n is 1 over n. The limit of that function is very easily 0. All right. So we've proven that it is decreasing and the limit is 0. Therefore, by alternating series test, A sub n converges, right? All right, let's try another one. Let me just check and see if I can see how many of these there are. There's only 4 of them. Okay. So we should be able to finish that up before the end of class for today. All right, so the alternating portion here is this. So when I take the absolute value, that piece disappears. So I want to graph 5n squared over 3n squared minus 2n and see what that looks like. And that is absolute value A sub n. And again, you could just plug in x there and see what it looks like. And yes, I understand it's discrete points, but we can still look at it as a full graph and get the idea. Alright, so if we look at the portion that starts at 1, that function, again, follows this trend. So decreasing. That's the first part. Second part is show that the limit of the absolute value of A sub n approaches 0. Again, choose the highest power of n in the denominator. So we get 5/3. Now remember, it said that the limit had to give us back 0. It does not do that. If that's the case, remember it says that we have to have both of the criteria. If we don't have both, diverges. Alrighty, 2 more to go. Yeah, apparently I already fixed it, Ken, but thank you. All right, so once again, once I take that absolute value, this portion right here is going to disappear, right? So absolute value a sub n is n squared over n cubed plus 4. Again, plotting that function. Let me zoom in here. Now this one I always liked because if you look at this guy for the graph, we get this. So you might panic and go, oh no, some of those terms are smaller than the ones that are that come next. Where is 1? It is, let's see, let me do my window from starting at x equal 1. So 1 is approximately here. But it's okay. If you notice, the directions were somewhat vague. So as long as a majority of the terms are decreasing, we are okay. So it actually passes the first part. Second part, limit n approaches infinity. N squared over n cubed plus 4. Divide by n cubed. When I do that, I get 0 over 1. That's 0. Passes that one too. Converges. And I believe the very last one's going to do the same thing. Yes, as long as it's decreasing for the majority, you're good. So let's look at this last one. The absolute value of a sub n is n squared over e to the n. Again, if you graph it, you get that same kind of behavior. We can still claim this is decreasing. And then we need that limit as n approaches infinity, n squared over e to the n. What do we do in this case? Any ideas? So if I plug in right away, what do I get? Looks like infinity over infinity, right? Does that cue you into what we should use? Maybe think back to Calc 1. All right, use L'Hopital's rule. So I've got to differentiate top and bottom. So that's now limit n approaches infinity to n over e to the n. Again, infinity over infinity. So differentiate again. 2 over e to the n. It's 2 over infinity. That's 0. Converge. Alright guys, so that's all I have for you for today. Let me stop the recording, but if you still have questions, you're free to ask them.